0 times 10 to the third.
Okay, that's what I was gonna just thought.
Or you can write it as 5,000.
I'll ask him about it.
On number 7?
Both of them?
I'll ask him about it.
Your initial was
Okay,
0.
the cups
Yeah.
have come in, and they're pretty cool because you can like lock them and then that pops up. By the way, if you drop them, ask one of my students in first block, this thing completely shatters if you drop it, like if you put it in your book bag, you swing it around and it goes flying across the room and it lands, this will break.
Oh no.
Oh yeah.
What do you know?
Anyway, so if you want one, it's a great deal. They're like $20 for stainless steel. And for those of you that, if you buy them, I'm going to have like 5 gift cards to Freddy's to give away and a drawing for those of you that buy them. So if you want one, it's a great deal. It's really, really nice. I used mine all weekend. Anyway, if you want to write a check, tell mom and dad to make it out to Mays High School. And so there's that. So not right now, but if you want one, it's a cool deal. So there's that. Or you can buy one for mom and dad and give it to you for Christmas. That too. Okay. Any questions on, where are we going? Honus?
Number 7? That's the desk one.
The what?
The one if you fall off one of the tables.
Okay, here's the deal. So on number 7, here's the setup. So you're standing up here, right? Okay, and you're going to fall. What's your initial velocity?
0.
0, okay? V naught is going to equal 0, okay? So, because you're just standing here and you're just going to fall. I'm not going to throw you down off the table. I'm not going to throw you up in the air. You're just going to fall. Now, here's where you run into trouble. And this is how you consistently do the signs on your gravitational acceleration. If you work this consistently, your signs will not give you any trouble. Okay, there will be no inconsistencies. But here's where you're going to run into trouble. You're going to go, okay, all right, let's say that you want to calculate the time. Well, you know that distance equals 1/2 AT squared plus V naught time. Okay, I don't have to worry about V naught because I'm going to fall. Okay, let's solve for time. All right, so you got time, square root of 2D over 8. Simple, this is good. Now at this point you go, okay, and I'm going to do this wrong. Do not do what I'm going to do. And I'm going to go, okay, that's 2 times 0.7 meters divided by a negative 9.8 meters per second squared. So what's wrong?
You'll have a negative under the radical.
Why is this going to be a train wreck?
You'll have a negative under the radical.
Okay, you're going to have a negative underneath the radical. And at that point you go, oh, I'll just pretend that's positive. You have to look at these problems in their entirety, okay? You can't cherry pick when you make G positive and when you make G negative. There's a simple solution. If you make the point where you fall off 0, okay, you make that the reference point, and then you're going down and you make that negative 0.7 meters, then if you take your final position minus your initial position, this becomes negative 0.7, and now you have 2 negatives underneath the radical. Hey, the problem is solved. Okay? Now, do I know if you're going to just ignore that and just act like it's not there? I'm not going, I can't watch over your shoulder and go, you know, hey, come on, make that a negative, okay? But if you view this as one big idea, and that's how you're going to be really successful with these problems, is if you view them as big ideas. So, if you make them both negative, the problem goes away. The same thing is true if you're going to find your final velocity. Oh, okay, v squared equals v naught squared plus 2ax. Okay, initial velocity is 0. And again, underneath this radical, if you make that negative 9.8 meters per second squared, and you make that negative 0.7, then you have 2 negatives underneath the radical. Hey, problem solved. Okay? So if you work the problems consistently, the problems take care of themselves. Okay? Is that?
I think so. So for the how fast would you be going? Is that like after the 0.7 meters?
Yeah, that's how fast you're going right at the point of impact.
Okay.
So that would
yeah.
be at like a given time, like a specific time you'd have to list, right?
Yeah, it's like when you hit the ground, after you fall on the 0.7 meters.
Okay.
Don't make this complicated.
All right.
Yeah. take this times negative 9.8 meters per second squared times negative 0.7, take the square root of that, boom, there you go. So on number 7, both of your answers on number 7 should involve a 3. Oh yeah, there's some other numbers, okay? But they should both involve a 3. Okay? Go with that. Anything else? Now, let's talk about number 15 with Bubba and Larry and Daryl. Okay, I want to make sure everybody's got that one. So, here's the bridge.
Sorry.
Okay? And we've got Bubba, and then Larry, and then Daryl, right? So, here's the setup. So you got Bubba. Bubba's just chilling out there. He's got a golf ball, which is a bowling ball in the problem, but it's the same idea. So I've got this, and he's just going to drop it. So what's the initial velocity of Bubba's bowling ball?
0.
0. Now, start with this. What do you know is going to happen as soon as he lets go of the bowling ball? What's it going to start to do?
It's going to accelerate downward.
It's going to begin to fall. Now, this is going to play into Newton's laws, which we'll get to on Thursday. By the way, big test on Wednesday, okay? Beauty of it is there's no new equations to learn. It's just applications of the same form, okay? Big test on Wednesday. Because Wednesday we're on a shortened schedule, if you want to come in early and start the test so you're not rushed, you can. Might come in, maybe 10 minutes early before, might have to give up party to lunch. But if you want to come in early on Wednesday to start this test, you're more than welcome to do so. Okay, so here's what you'll see out of what's Newton's first law of motion. Newton's first law of motion basically says Mother Nature is lazy. Mother Nature does not want to change a velocity vector once it's established. So here I am holding this golf ball. As soon as I let go of it, it begins to accelerate. And this goes under this whole idea of Jedi-Stoffel law. You stop the force and watch what happens. So as soon as I stop applying this force, okay, and I observe what happens, that ball begins to accelerate. The only way that can happen is if there is an external force acting on the ball. Because Mother Nature says, wow, that thing doesn't have a velocity vector. I'm just going to let that thing chill out. But as soon as you see a velocity vector happening, you know a force has to be acting on it. Because for lack of a force, that ball will just hover. So imagine if I could have a gravity switch on, a shut off gravity the second that I let go of this ball. The ball is just going to stay there, okay? Because there would be no force to make it accelerate, because Mother Nature says, hey, you're chilling out, you don't have any velocity, hey, fine, go ahead and chill out. Why do I care, okay? But when you begin to see that force and you begin to see that acceleration, you know something has to be happening on it. So, Bubba's is the easy one. So on the velocity time graph, where is his line going to start? Hunter, where's his line going to start?
At 0.
What?
Because he doesn't throw it up or down.
Okay, so what's the line? The line's going to do one of two things. It's either going to slope up or it's going to slope down.
Yeah.
And what's the value of that slope?
And 9.8.
Beautiful. Okay? Negative 9.8 meters per second squared. Okay? So there's Bubba's. Right? Now, you go to the next one. Right? So Daryl is going to, or Leroy drops it. Bubba throws it. So he's going to throw it up in the air at 10 meters per second. Now, his is going to start up here at 10 meters per second. But go back to that idea. As soon as it leaves his hand, what's the only force acting on it?
Gravity.
Gravity. And what's the ball going to do as soon as it leaves his hand? It's not going to go down. It's got to do something else
Its
first.
velocity vector.
It's got to slow down,
Change it.
stop, then change the direction, and then
Speed up.
speed back up. So we're going to show that by a line coming down like this. But what's the slope of this line?
Negative 9.8 meters per second squared.
Negative 9.8 meters per second squared. Because what's the only force acting on it after it leaves its hand?
Gravity.
Gravity. Guess what? That's going to create the exact same acceleration. Ah, okay. Kind of cool. Now, when is this ball going to change direction?
And it crosses 0.
It's the x-axis.
when it crosses 0 meters per second. Okay, so this is the only one that's going to have a direction change. So, now the third one, Daryl. Daryl has anger issues. Okay, so Daryl says, screw it, and he throws his ball down. Okay, bit of a temper tantrum, right? So, where's his ball going to start? Negative 9.8, or negative 10 in this case, right? Negative 10. But then what's it going to do?
Go down.
It's going to go on the exact same slope as the other three. Because as soon as it leaves his hand, the only force acting on it is gravity. That's it, nothing else.
So why can't you illustrate that it goes from 0 to 10 first, like for the one that gets thrown into the air? Wouldn't you have to draw that as go from 0 to 10 first? And
Yeah, but we're just not going to worry about it.
It's not
We're just starting it at, like from the point that he lets go of it.
Oh, okay.
And this one would have to start at 0 and technically go down to negative 10.
If I had that, would that be all right?
No, you're fine. The main thing I'm going to look at is that after it leaves her hand, these are going to be the slopes of the lines and that they're parallel.
Okay.
That's the main thing that I'm looking at. Okay? The one with the hailstone, that should be over like 400 meters per second,
Yeah.
which is really, really, really fast. So if you, and thank God that isn't what happens, because this is neglecting air resistance. So in reality, if you've ever seen cars that are damaged by hailstones, those hailstones are hitting at about maybe 15 to 20 meters per second, depending upon your atmospheric conditions. So if you see the damage caused by hailstones that are going 15 to 20 meters per second, imagine if they're going at 400 meters per second, which is faster than the speed of sound. Like you wouldn't have like dents in your car, you would not have a car. Because literally, I mean, it would be like getting hit with high-speed bullets. There was that much kinetic energy. It wouldn't dent your car. It would blow holes completely through your car. Okay, it was just gone. Right, roofs on your houses, gone. Okay, just shredded. Yeah, you don't want to be out in it either because you're going to get hit with one and.
What would that do to the ground?
Huh?
What would that do to the ground?
It would make it so
Oh
everything's
yeah,
analyzed.
well, but the irony of it is, without an atmosphere, we wouldn't have hailstones to begin with because we wouldn't have weather. So it's kind of a catch-22. But yeah, this is like a purely hypothetical thing. Is that you just leave out the friction, all that good stuff. Now let's talk about number 14. With the pyrotechnic device, when do you want that thing to explode? At the top or at the bottom of the flight?
At the top.
Yeah, bottom of the flight's bad. Somebody's going to get sued. Okay? That's true. And you want the ooh-ah factor, right? You want it up there to go, ooh-ah, pretty. Okay?
Do you not enjoy the scream factor when like you think you're gonna get hit by a mortar and you gotta run?
What?
Do you want to
That's
hit
part when
a
they
young
malfunction,
child?
they fall before they explode, so you think you're gonna get hit and you have to run.
It's not fun.
What
A lot
sketchy
more fun
pyrotechnic
than the
devices
ooh-ah
are you
factor.
using?
Okay, anyway, here or there. So anyway, so what you should see on 14, there's only one way to work 14A. And only one way to work 14A. And that's to use distance equals 1/2 AT squared plus V naught time. That is the only way to work this problem. Now, what some of you are tempted to do is you're tempted to use this. Okay? You're tempted to use this and find distance that way. But here's the problem. You don't know what the final velocity of the mortar is. Okay? You don't know. Okay? So you cannot use this equation because you don't know the final velocity. Everybody goes, oh, it's 0. No, it's not, because I did not tell you that the mortar exploded at its maximum height. All you know is that it exploded after 5 seconds. Okay? That's the only thing that you know. I never said, oh, it exploded at the peak of its flight. I never said that. I just said it exploded after 5 seconds. Now, here's the bigger idea. Let's say that gravity was just a little bit stronger, and because the mass of the Earth was bigger. And let's say that instead of having a gravitational acceleration of negative 9.8, let's say it's negative 10. Okay? So it's like, and again, if you go with this analogy, you show up to the store and you have $50. And you have to spend $10 per second. How long is it going to take you to run out of money?
5 seconds.
5 seconds. So if you consider, just as a round estimate, okay? The initial velocity is 50. If g was negative 10, okay, it would take about 5 seconds to reach maximum height. So you got to figure that this ball, when it explodes, the mortar, when it explodes, is somewhere around 0 meters per second, which makes sense, right? That's when you want it to explode, is when it's near the top of the flight. So if you look at just getting an idea, it's like, oh, okay, well, if g was negative 10, it's going to be at about 5 seconds, which makes sense. That's when you want that mortar to explode. So the only way you can figure out that velocity at that point is to use this v equals v naught plus at. And I beg of you, do not get wrapped up into the equations game. The test on Thursday or Wednesday is going to be a train wreck if you do. You have to look at problems in their entirety. You do not play the equations game. The equations is like the last step. Look at what's happening. Oh, okay, right. What's this? We don't want this thing to explode. Okay, near the top. Velocity, probably something around 0. Okay? So that's what you want to look at. Let me see. Your answer to number 9 should be around 35. On number 4, with the super tanker stopping, both of your exponents on number 4 should involve a 3. One of them is going to be 10 to the negative third, and the other one's going to be 10 to the positive third. Number 4.
Oh, you're talking about like scientific notation.
Yeah, if you put it in scientific notation. Yeah.
I did something.
One's going to be 10 to the negative third, one's going to be 10 to the positive third. If you put it in scientific notation. Talk to me.
Can I ask you about 12C when you asked to graph it?
Yeah?
They would both have the same velocity.
Yes.
I just don't know how it would look on the graph.
Well, let's figure that out, shall we? Okay, so here's the velocity time, right?
Yeah.
So what you should, let's make sure this is right, because if this is wrong, everything else is wrong. Your answer to 12A, listen to me, should be around the legal drinking age. Not what you think it is when mom and dad are out of town. Okay? Not that any of you would do that. I'm just, your friends might. Okay? Just saying, asking for a friend. Okay? So anyway, so that should be, and it's like, what is the legal drink? Should be around 21. Okay? So what I'm looking for on C is this. So you're going to start up here around 21 meters per second. So as soon as it leaves, what's this line going to do? Yeah, it's going to come down like this. So call this your Earth line. Okay? Sounds kind of hippie-ish. Here's our Earth line. Okay? So here's the deal. You're going to go to the moon. It's going to start with the exact same velocity. So it's going to do one of 3 things. Your Earth line is going to be the exact same as the moon line. Okay? And you would label it that. The moon line is going to be steeper, or the moon line is going to be more shallow. That's what you got to figure out. Okay? Anyway, on number 3, there should be roughly about 10 meters per second squared difference between your 2 answers on number 3. That's an ish, okay, but there should be a difference of about 10. Make sure you tell me which one is bigger. Now, let's clarify one thing. When you get to number 5, okay, and you drop the ball, here's one of the most important things that you have to understand. So here's the bridge, here's 0, you're going to drop this thing, you're going to look at what happens after 1 second, 2 seconds, 3 seconds. So one of the most vital things that you have to be able to do is look at a value and see if it's a linear or if it's a quadratic relationship. So if you look at the change in the velocity, you have v equals v naught plus at, right? On this one, what's your initial velocity going to be? This is on number 5. What's the initial velocity? 0. You drop the ball, right? Okay? So you don't have to worry about this. So as soon as you see it's just acceleration times time, you know this has to be a linear function. Because the only thing that changes is you plug in 1 second, 2 seconds, 3 seconds, 4 seconds. Okay, that's it. It's a linear function. Now, if you look at how far it falls, that's 1/2 AT squared plus V naught time. So that one, your initial velocity is going to be 0. So here's the difference. On how far it falls, now it's t squared, which means it's going to be what? Linear or quadratic?
Quadratic.
Quadratic. As soon as you see a constant acceleration multiplied by time squared, it cannot be a linear function. Okay? Now, so here's how this all fits together. On number 5, this is what your velocity time graph should look like. What's the slope of the line? Negative 9.8 meters per second squared. Cool, right? Life's good. Okay? Negative, so it's like this. You go to the mall, you're spending $9.80 a second. You walk in with no money, but yet you still spend money. So, at the end of 1 second, how far into debt are you? $9.80. At the end of another second, guess what? You're in debt another $9.80. Okay? So for every second that goes by, this is how far you're going into debt. Now, here's the kicker. And this is where you have to understand how all of this fits together. If you go to your position time graph, and your position time graph should be a nice quadratic function, okay? If you go out to 1 second on your position time graph and you drew a tangent line, what would the slope of that tangent line be at exactly 1 second?
Negative 9.8 meters per second
Why?
squared. Because after 1 second, that's what your acceleration is.
Exactly. At the end of 1 second, you're going negative 9.8 meters per second. At the end of 2 seconds, you're at negative 19.6. That line's going to get steeper and steeper and steeper. So your slopes of your position time graphs gives you instantaneous velocity. Now, for those of you that are calculus nerds, if you take the derivative of this, okay, you have 1/2 AT squared, multiply by 2, reduce that exponent by 1, then you get acceleration times time, and that's why that's a linear function. And then if you take the derivative of that a second time, it becomes just the constant of acceleration. So, if you're not taking calculus, that makes no sense to you, and God bless you. So, it's evil. Okay. Anything else? Going once. Going twice. So, put that in down. Like and subscribe. Did you zoom in on that?
It's back there. Here, let me zoom in on that so I can get my intro.
Yeah, here.
So I can give an intro.
Yes.
Yes, like and subscribe.
Hey guys, what's going on today?
Filmed in front of a live
Hey
studio
guys,
audience.
back
What's
with,
going on, guys?
you're back with Bergie Berg for another episode of Honors Physics.
What's up, guys?
With Bergie Berg. Dumb name. Dumb name.
Can we get 1,500 likes on this one, please?
Smash the like button.
Gotta get 1,500 likes.
And
or I'm gonna be
roll the
real
outro.
disappointed.
All right, episode's over.
It would be. It would be.
It's filmed in front of a live
That way I
studio
don't have to
audience.
sell plasma on the weekends. I'm kidding.
Why are you, like, what's so bad about that?
No,
Nothing.
I have enough things to do in the
Yeah,
weekend.
but some people.
Okay, so here's like the last kind of culminating problem out of this whole gravity thing, okay? So imagine that we're going to take a ball and we're going to throw it up in the air and we're going to time it from the point that you let go of it until the time that it lands, okay? So you go start, stop, boom. Total time is 2.20 seconds. That is the only time that you know, okay? That's the only value, 2.20 seconds. You know nothing else. So from that, I want to calculate the initial velocity of the ball, the maximum height of the ball, the velocity and height at 1 second, the velocity and height at 2 seconds. I want to draw the position time graph, the velocity time graph, and I want to figure out the slope of the tangent line on the position time graph at exactly 1 second. Okay, so I want to figure all of that out with one number, 2.20 seconds. That is the only number that you were given. Now, let's just look at the big picture. So what do you know has to happen to the velocity? Oh, catch that. Whoa, who could bounce? What do you know has to happen to the velocity of that ball? What does it have to do?
Decrease.
It has to decrease, then it has to stop, then it has to
Speed up again.
increase, and it's going to change sign, right? Okay? Is the velocity ever going to be constant?
No.
No. Now, we're not including the toss, and we're not including the catch. So this is from the instant that I let go of it until the instant that it gets back to my hand. Now, think this through. As soon as it leaves my hand, what's the only force acting on it?
Gravity.
Gravity. The acceleration caused by gravity is going to be?
Negative 9.8
Beautiful.
meters.
Now, whatever you do amongst my list of pet peeves, do not tell me, oh, gravity is negative 9.8. That is so just incredibly wrong, okay? Gravity causes an acceleration of negative 9.8 meters per second squared, okay? But gravity is not negative 9.8, okay? Don't say that. It's just bad form. Don't say that. Okay. Now, what you'll see is that if you screw up V naught, everything else you're going to do is going to be wrong, okay? So let's make sure that we get that V naught calculation right. So let's actually start with the position time graph. So here's my position time graph. Olivia, what's my position time graph going to look like?
It's going to be like a window.
I like that. Something like this?
Yeah.
Where's it going to be at 1.10 seconds?
At the top, like very top.
Beautiful. And what's the slope of that tangent line going to be, Olivia?
0.
Why?
Because it's stopping before changing direction.
Beautiful. Okay, spot on answers. So here's the deal. If it returns back to the same height, you can assume that the flight is symmetrical. Time up is going to be the same as the time down. Okay, it's going to be symmetrical. That's cool. 1.1, this is going to be out here at 2.2, right? All right, it's nice. Tangent line, like Lydia said at the top, is going to have a slope of 0. We're off to the races. Now, what's the velocity time graph going to look like? Just generally.
Just a line like that.
Line like this. Okay. Doink. That's the sign you need to make when you draw this. Doink.
Yeah.
Okay.
The doink graph.
Doink. So, Garrett, where's the ball at that point?
At the top,
Why?
because it's 0.
Beautiful. My velocity is 0. I'm slowing down. I hit 0, then I start to speed back up. Nice. So this is going to be at the top. What's the slope of the line going to be?
Negative 9.8 meters per second.
Beautiful. I have hope. Okay, negative 9.80 meters per second squared. Now, this is going to take 1.10 seconds. So here's my question. Okay, here's the $1 million question. Is my initial velocity going to be exactly 9.8 meters per second, bigger than 9.8 meters per second, or smaller than 9.8 meters per second?
Bigger.
In my initial velocity.
Small.
Slightly bigger.
Slightly bigger. Because if it was 1 second, then it would be 0. It would have to be.
If-
It'd have to
if-
be 0 at 1 second if it was 9.8 your initial.
Wait, initial, I thought you were just throwing the ball up.
Yeah.
So
Yeah.
it
So
starts
it
at
has to
0.
be bigger.
But no,
No.
this is right as it leaves my hand.
Oh, right, okay, sorry.
It has to be bigger because it is going up and then it slows down.
It takes more than
That
1
is
second.
true.
To 0.
It takes more than 1 second for it to get to 0.
But here's the deal. Think this through. All of you are right. Let's just kind of consolidate what you all were saying. Okay? I'm going to throw it up in the air. So what's the sign of my initial velocity? Okay. Now, think this through. This is like you're going to the mall and you have positive cash flow. Okay? Your 3 favorite words as you get older. Positive cash flow. Okay? Your next 2 favorite words are going to be disposable income, because that allows you to buy cool toys. Okay? So you want positive cash flow and disposable income. Okay? It makes life better. All right. As has been said, money cannot buy happiness, but it makes it easier to be happy. Be sad. No, it's true.
It is true. What'd you say?
This isn't anything.
I didn't hear you.
What?
What'd you say? I didn't hear you.
I said, money cannot buy happiness, but it makes it easier to be happy.
It's true.
Okay.
Money buys food, food makes everything better, so.
Yeah, it buys them McGriddle sandwiches,
Right.
and it's all good.
Can't be happy if you don't have.
And you'll be happy. Okay. That's why they call it a happy meal, not the sad meal. There's the marketing right there.
They should call
Hi,
it obese.
welcome to McDonald's. Would you like a sad meal? Sure. Okay. All right.
Or just tell me
Or
what
how
you
about a
did.
just okay meal?
Mediocre meal.
Yeah, mediocre meal. Okay. Now, think about this. You go to the mall and you have exactly $9.80, and you have to spend $9.80 per second. So how long is, if you had exactly $9.80, how long would it take to spend the $9.80? Exactly 1 second. Now, you know it takes a little bit more than a second for you to go broke. So, that means you had
A little bit
A
more.
little more.
a little bit more than $9.80 when you went in the mall. A lot more?
No.
No. Okay? It wasn't a lot more because of the fact that it only takes you a little bit more than a second to run out of money. Cool with this idea? Okay. Now, so I know this number up here has to be greater than 9.8 meters per second, but just a little. Okay? Not a whole lot, just a little. We're going to go to 0, and then down here, we're going to land. What do you know about this velocity when it lands? What's the sign going to be? Negative. Why?
Because it's going
Because it
downward.
changed direction.
Change direction, it's coming back down. Now, this one's going to be a little bit more than negative 9.8. Now, let me make sure everybody's cool with how physicists view negative numbers versus how mathematicians view negative numbers. If you're in a math class and I said, which one is greater, -1 or -300? Which one's in a math class? Which one's bigger?
Negative 1.
-1. Why?
Because
Because it's close to 0.
Closer to 0. Okay, standard answer. But here's my question. I'm going to throw this golf ball at you and I'm going to hit you in the arm. You can pick one of two velocities, -1 or -300.
Negative 300.
Yeah, I'm guessing you're going to pick -1. -300 would be close to the speed of sound. Okay?
oh,
Dude, I have a sweet hole in my arm then.
No,
Oh, yeah.
I'll get a sweet
Because
ball.
that's
at
not,
home.
I got a sweet hole, but no.
you'd be in the MLB.
People can live without their arms.
I know, but
No,
I really don't think you
You
want to
just,
take one for the
you
team
would
on
have a
that.
hole in your arm. You just
I
whip the
appreciate
time.
your willingness to do
Just
so,
be
don't
gone.
get me wrong.
Imagine if you just had a golf.
So, here's my point. In physics, -300 is going to be faster than -1. Okay? So when I say this is going to be greater than -9.8, I'm talking like -10, -11, something like this. The negative sign is just indicating the direction. Okay? So don't let your math training get in the way of learning physics. Okay? All right. So, here's the kicker. We know that velocity, the initial velocity has to be positive and has to be a little bit bigger than 9.8. Now, Vonda, when it reaches that maximum height, what's the velocity going to be?
0.
Beautiful. And I know my initial velocity is going to be a positive number. And I also know my acceleration of -9.8 meters per second squared. So here's my question, Vonda. What equation relates initial velocity, final velocity, acceleration, and time?
On the list,
On the list.
which is v equals v naught times plus 1/2 acceleration.
No. No. You make this way complicated, Vonda. I want that relates velocity, velocity final, acceleration, and time.
Oh, wait. The first one?
Yes!
Okay.
Beautiful. So, V equals V naught plus AT, right? Good?
Yes.
Okay, don't make this complicated, okay, because we don't know how high it's gone at this point, okay? I don't want anything that involves distance. So, here's the deal. Do you know the final velocity on the way up? Sure you do. What's the final velocity on the way up?
0.
Goose egg, right? Do you know the acceleration on the way up?
Yes.
Yeah. You know the time it takes to get to that maximum height?
Yes.
What's the only thing you don't know?
V initial.
V naught. So if I take V minus V naught, right? Excuse me, V minus AT, my bad. Hold on. V minus AT is going to get me V naught. And now, again, if you do this right, the signs will take care of themselves and you don't have to do anything weird or hinky with them. So on the way up, my final velocity is going to be 0 minus a negative 9.8 meters per second squared times 1.10 seconds. So this is why you have to pay attention to the signs and work this in this sequence. So I've got 0 minus a negative number. Guess what? That's going to give me a, and that's what we said V naught has to be. We said V naught has to be a positive number. So somebody take 9.8 times 1.1. It's 10 something.
10.9, or 8, sorry.
10.8
Yeah.
meters per second. So at this point, now I know my initial velocity. Logan,
Why is the time 1.1 not 2?
because 2.2 is the entire time to get back to my hand. It's going to be at that maximum height halfway through the flight. Does that make sense? Okay. Go with this. Now, does it match what we said was going to happen? We said it was going to be a little bit bigger than 9.8. We said it was going to be a positive number. We're cool. Now, here's how can you take this and make sure that you're right? What could you do to make sure that that V naught value is right? Yeah, you can try and find time. If you take 0 minus 10.8 divided by negative 9.8, you should get 1.10 seconds. Or you can calculate the acceleration. Take 0 minus 10.8 divided by 1.1, see if you get an acceleration of negative 9.8 meters per second squared. If you did, it's right. If you don't, I promise you it's wrong. Okay? So when you get done, if you have the time and the inclination, go back and go, wow, does this whole deal make sense? So, if this is 10.8, so let's kind of clean things up a little bit. So, on your velocity time graph, we're saying we're starting up here at 10.8 meters per second. That's 1.10 seconds, and that's going to be so, here's one of the most important parts that you have to understand in terms of terminology, okay? So on the test on Wednesday, when I ask you questions about a ball thrown up in the air, you have to be able to differentiate between speed and velocity. Speed is just how fast it's going, it doesn't indicate direction. So when I throw this ball up in the air, when does it have its greatest speed?
The instant that it leaves your hand.
Just going down, or just when it leaves my hand? Or both?
Both.
Be both. So it's going to have the same speed when it leaves my hand as when it returns back to my hand, if it returns back to the same height. Now, if I throw it up in the air, okay, and I let it fall all the way to the ground, the two speeds aren't symmetrical. But if it returns back to the same height, that's a huge caveat. If it returns back to the same height, the two speeds are going to be the same. Are the velocities going to be the same?
No.
No.
No. What's going to be the difference?
The sign.
Yeah, one's going to be positive, the other one's going to be negative. So if a ball returns back to the same height, the speed's the same, velocity's the same, but the velocities have opposite signs. Okay? Good with this. Okay. Now, if you don't believe this is negative 10.8, it's like, oh, Mr. Burkamp, how did you get that? Did you just make up the numbers? Seriously, how are we supposed to believe these things? Okay. On the way down, what's my initial velocity?
0.
0. So then I can go, okay, V equals V naught plus AT. So let's find the velocity on the way down. So on the way down, my initial velocity is 0. And then I've got a negative 9.8 meters per second squared times 1.10 seconds. Guess what? I'm going to get negative 10.8 meters per second. Okay, if you don't believe me, there's the math. So I'm going to start it at 10.8. I'm going to go to 0. I'm going to end up at negative 10.8. Same speed, opposite signs in the velocities. Cool with this. We're good. Now, let's talk the calculation of, that V naught is 10.8 meters per second. Okay, that's cool. Now, let's talk maximum height. There's a whole bunch of different ways that you can calculate maximum height. How you do this, I do not care. So, how can I take my velocity time graph and find my maximum height?
Area.
Area, okay? Oh, this looks like a triangle, right? So, area of a triangle. That's in my wheelhouse. 1/2 base times height. You know the base?
Yeah.
Know the height.
Yeah.
Area of a triangle. Boom, there you go. I like it, okay? So, somebody take 10.8 times 1.1 and then take half of that. Or take 0.55 times 10.8.
5.94.
5.94?
Yeah.
Okay? Now, to give you some perspective, this ceiling is about 2.5. Okay? So it'd be roughly about a little bit more than twice as high as the ceiling. Okay? Just so you have an idea of how fast, how far that goes up. Okay, so that's if I like triangles. What formula could I use to find the maximum height? Tori. Oh, come on.
I was just gonna do a triangle one.
Oh, we already did that one. Tori, you know the initial velocity on the way up?
Yes,
You know the final velocity on the way up?
yes,
You know the acceleration on the way up?
yes.
You know that v squared equals v naught squared plus 2ad?
That equals.
Oh, that equation. That's
Yeah.
kind of cool, right? So the other option is we could go with what I eventually got Tori to say, okay, is that Tori realized, oh, we could use v squared equals v naught squared plus 2ad. You know, everything except for
Ton.
the acceleration, everything except for the maximum height. And guess what? You get 5.94 meters. Okay? Yes?
Could we use any of the other, like d equals 1/2?
Oh, yeah. Oh, yeah. Oh, we're not done.
Okay.
Oh, we're not done. Okay? Oh, we're so far from being done. So, like Logan said, we can go, oh, distance equals 1/2 at squared plus v naught time. Do you know the initial velocity?
Yes.
When does it reach maximum height?
1.16.
1.1 seconds, so you know that. You know g is negative 9.8 meters per second squared. You could do that. Legitimate. You could also, wait for it, do distance equals 1/2 v plus v naught times time. You could do that one. Okay? Like I said, there's like 4 different ways you can find the maximum height. I don't care. Pick one. But here's what's important. Every one of them involves the initial velocity. And if the initial velocity is wrong, everything else is going to be wrong. Okay? That's why it's so important that you have the initial velocity be correct. Okay, good with this. All right. So, we've got maximum height was we're going to get 5 point what?
9.4.
Okay, 5.94 meters. All right. Okay. So velocity and height at 1 second. Now let's talk about this before you do any calculations at all. Okay, before you even lay hand on a calculator. Is the velocity on the way up, Landon, going to be a positive or negative number?
Positive.
Why do you know?
It's going up.
Huh?
It's going up.
How do you know it's going up? When does it reach its maximum height?
When velocity becomes 0.
How much time does that take in this problem?
1 second.
Well, 1.1, right? So it took 1.1 seconds to reach the maximum height of 0, right? That's when the velocity goes to 0. So 1 second into this flight, which direction does it still have to be going? Up, because it's still going to be a positive velocity. So I know I'm still going to, that height is going to be, or that velocity is going to be a positive number. It's going to be probably pretty close to 0. Yeah, because it's going to reach 0 at 1.1. So this is real, real close to the top. Now, let's talk about the height and how high it is at that point. Maximum height we said is 5.94 meters. So, at 1 second, could my height be greater than 5.94?
No.
No. Why?
No, it's 1.1 seconds,
Yeah, at 1.1 seconds is when it reaches its maximum height. Is it probably going to be pretty close to it?
Very good.
Yeah, it's going to be pretty close, but it's not going to be 5.94, but it's going to be close to it. So again, without doing any calculations at all, you can get an idea of how this problem is going to play out and what your answers should be. So, how can we figure out the velocity at 1 second? Now, if you think about it, I gave you a duck because I chose exactly 1 second. Why does that make it easier since I chose exactly 1 second?
Because you just said negative 9.8, right?
You don't necessarily even need.
Yeah. But you could just use v.
Just use the first equation.
Yeah, v equals v naught plus at.
Yeah, you could use the first equation, but here's the bigger picture. How much money do you have when you walk in the mall?
5.
$10 and
86.
how much do you spend per second?
$9.8.
$9. So you walk in and you have $10.80. At the end of 1 second, you spent $9.80. How much money do you have left? $1. Boom, there you go. Okay, that's it. You have $1 left. So here's the importance of this. And again, do not get so wrapped up into the equations that you lose track of the big picture. So if you look at this velocity time graph, okay, here's 1.1. So you started at 10.8. So here's the big idea. Every second that goes by, how much does your velocity change? 9.8. Oh, I'm down like this, right? I'm not quite 1.1, but I'm pretty close. So I know I'm going to have a small positive velocity. Now, if you like equations, oh, look, V naught, 10.8 meters per second, plus negative 9.8 meters per second squared times 1 second. Yeah, you got 10.8. You subtract negative 9.8, you get 1. Okay. Now, so here's the cool thing. If you were to draw that position time graph, okay? If you were to draw that position time graph, and you were to come out here at 1 second, there's 1.1. What would the slope of that tangent line be in exactly 1 second?
1 meter.
No. What would the slope of the tangent line be at 1 second?
1 meter per second.
1 meter per second. Why?
Because you have 10 meters.
Because that's how fast it's going at the end of
1 second.
1 second. So this line would have a slope of, and then we've got 0. Okay, we're approaching that. Cool. Now, at the end of 2 seconds, so here's 2.20. Now I want to look at 2 seconds. So right away, what do you know about the sign of the velocity at 2 seconds?
It'll be the same, just a different sign.
No.
Say the question again? I gotta sign it.
It'll be
I say again, no.
Yes?
So yes.
So here's the deal. In 2 seconds, if I'm going to tell you straight up on the test. I'm going to give you a problem like this. I'm going to say, what's the slope of the position time graph at a point in time? So what am I asking you to find? Even though I'm asking you to find the slope of a tangent line, what am I asking you to find?
Velocity.
The velocity, the instantaneous velocity. That's it. Don't flip out and go, oh my God, I draw a tangent line. No, it's not the point. Okay? It's not the point. So if you go to the 2 second mark, okay, at 2 seconds, look at it this way. At the end of 1 second, you had spent $9.80 and you were left down to $1. At the end of 2 seconds, how much more money are you going to spend? You're going to spend another $9.80. Are you going to be in the hole?
Yes.
Yeah. By how much?
$9.6.
$8.80. Okay? Because you had $1, you blew through it, and now you're in debt, and you keep spending. Welcome to Americans' consumerism, because nobody stops when they run out of money. So, at the end of 2 seconds, guess what? That velocity is going to be negative 8.80 meters per second. So this is why, grade what you said. If I come out here at 2 seconds, the slope of that tangent line isn't going to be the same as it is at 1 second, because it isn't symmetrical at that point. Okay?
I meant like on the other side.
Oh yeah, yeah. If you come over here, yeah, that would be symmetrical.
Yeah.
That's spot on. That is true. Okay, now, in terms of how high it is, here, to figure out the height at 1 second and the height at 2 seconds, there's only one way and only one way and only one way to work that problem. What's the one way you can do that problem? No, not that equation. No, you cannot use that equation. Do not use that equation. Do not use that equation. What can you do?
D is equal to B naught T plus 1/2 AT squared.
Yeah, use that function equation. The only way you can figure out that height, the only way you can do that is to use distance equals 1/2 AT squared plus V naught time. You know your acceleration, negative 9.8 meters per second squared. You know V naught, which was 10.8 meters per second. So the only thing that you can do is plug in the different values of time. Plug in 1 second, plug in 2 seconds, whatever time I give you. So don't confuse the points on a position time graph versus slopes on a position time graph. So these points tell you how high the object is at that point. Your tangent lines tell you how fast it's going at that point. Okay, so don't confuse the two. Got it? Good, Grant? Okay. Shut that off. Let me hand out the line.
Coach Rolex, he was wearing a robe earlier.
Yes, Mr. Bots is dressed up. I
It's
love
just not my
Doctor.
it. Yeah.
Too old fashioned for it.
style. Darn straight I am,
My bad.
Skippy. Okay. Generation Day, I'm in it. You know, I'm with you guys on the seniors. Okay, so let's jump forward to page 3. So here's what you're going to do in terms of the collecting the data. So listen to me very carefully. What you're trying to do on page 3, and this is the lab portion of this, you're trying to determine an experimental value of gravitational acceleration within this room. Listen to me. Do not in any way, shape, or form on page 3 use negative 9.8 meters per second squared for any calculation until you get to the end when you're trying to find the experimental error. And I even tell you up there at the top in big bold letters, do not use negative 9.8 meters per second squared in any calculation except for the end. So here's what you're going to do. Take either a golf ball or a tennis ball, normal groups, and you're going to try and bounce this thing off the floor so it gets as close to the ceiling as you can without actually hitting. So maybe something like, that was
Oh my.
that wasn't bad. Come on.
Oh.
That was varsity there. Okay, so what you want to do is time it from bounce back to bounce. Okay? So you need a couple people timing, one person throwing it, and then somebody standing up here to observe it. If you really want to go varsity, you can take your phone and put it like in slow motion and record the ball as it goes up against the backdrop of the meter stick. Okay, and so that way you can see exactly what that height is. That's if you really want to step up to the plate, you can do that. So here's all the data that you need. Bounce to bounce, boom, that's it. Okay, that's all the data that you need. But then you're going to record that maximum height. So then from that, you're going to calculate a whole bunch of things. Now, if you look down on the procedure on number 6, I said, show every step of every calculation. I refuse to guess what you have done. Everybody's data is different. So help me, as soon as I see any point where I lose track of your calculations, at that point I quit grading, okay? This is not about an answer, this is about showing me that you understand how this process works. So literally, as soon as I lose, if you just say, well, I'm just not write anything down, guess what? At that point, I check out, okay? Not gonna grade anymore. This is about a process. Now, let's say that you go, wow, I don't know how to do this. Let me give you a hint. Go back and look at the very first lap that you all did when we started the acceleration unit. You pushed the cart up the hill, right? It rolled up the hill, and then it rolled back down. And you measured the entire time, and you had where it started and where it ended up, and from that you calculated velocities and accelerations. So if you're not sure how to handle this, go back and look at that very first lap, okay? Use the resources that you have available to you. There's about 3 or 4 different ways that you can work this problem. I don't care, okay? I honestly don't care. All I want to make sure is that I understand what you have done. So if you're not sure if you're showing enough work, give it to someone else in this class, okay? You all know how I'm going to grade this thing. You all know my expectations. So if you're not sure, take it to someone else, say, what's Burkamp going to do? If they go, oh, Burkamp's going to flip out, it's probably not a good idea to hand that in. So I'm just telling you, show lots of work. Now, let me back up. Problem number 4, okay, on the front. Here's the setup. Problem number 4 is the exact same type of problem that I just worked. The only difference, instead of being 2.20 seconds, the entire time is 4.4. That's the only difference. All the other procedures are the exact same. Now, if 4A is wrong, everything is going to be wrong. So listen to me very carefully. Your answer to 4A should be around the legal drinking age in Kansas, okay? The legal drinking age, not what some of you think it is, okay, or what you think it should be. It's not it. Now, when you get down to D, you're going to sketch a position time graph, okay? You're going to sketch a position time graph. And I'm asking you, what's the slope of the line at 0, 1, 2.2, 3, and 4.4? What am I asking you to find relative to that position time graph?
Velocity.
Velocity. All I'm asking you is what's the velocity at time 0? And I tell you, don't actually draw the lines, okay? Don't draw them. That's not the point, okay? When you get to question number 8, imagine that you have 2 spaceships, one that looks like a remote control and one that looks like 1 kilogram mass. They're at the same point in space at the same time. One of them is traveling 450 meters per second, the other one is traveling at 600. So here's the setup. They're both at the same point in time. They're both going to go out, stop, and then they're going to come back to that same point in space exactly 86 seconds later. So they're starting here, they're going to go out, and they're going to come back. So how long is it going to take for each ship to stop? No, that's when it's back. 43 seconds. Because it's going to take 43 seconds to stop, 43 seconds to get back to that point. Now, I tell you on number 8, you're going to draw a velocity time graph. Do that. Label which one's Columbia and which one is Enterprise so that I know exactly what's going on. Now, when you get to number 9, here's the setup. You got a model rocket that looks like a remote control. You're going to fire the engines. What's the initial velocity of the rocket? 0. Okay? The initial velocity of the rocket is 0. It's sitting on the launch pad. Now, here's what's happening on number 9. Visualize this. Here's the rocket. That rocket with the engine firing is like me throwing this ball up in the air. Okay, that's when it's in contact with my hand. So I'm here, but as soon as it leaves my hand, what's the only force acting on it? Okay, so here's the deal. On number 9, you're starting with a velocity of 0. Once it reaches a point of 30 meters above the ground, it's going 75 meters per second. You're going to figure out the acceleration, and you're going to figure out how long it's going to take for that to happen. Then I'm going to shut off the engine. So that's like me throwing this ball up in the air at 75 meters per second. If I throw that ball up at 75 meters per second, what's that ball going to do? immediately after it leaves my hand.
Slow down.
It's going to start to slow down at a rate of, you show up to the mall, you've got 75 bones. You got to spend $10 a second. Roughly how long is that going to take to go through your money?
7.5.
About 7.5 seconds. So you got to figure the time from when you shut off the engines until it reaches its maximum height is going to be around 7.5 seconds. Ballpark. Okay? Yes?
Would the acceleration on mine just be -9?
Yeah. After you shut off the engines. After you shut off the engines. Okay? But initially you have a positive acceleration because that's like me throwing this ball up in the air. While it's in contact with my hand, it has positive acceleration. But once it leaves my hand, it has negative acceleration. Okay? All right, then on number 10, there's a bunch of stuff that you need to draw on this velocity time graph. So here's the deal. You need a position time graph for the ball. You need a velocity time graph for number 8. You need a velocity time graph on number 10, and then you need a position time and velocity for the lab. You're going to have a whole bunch of graphs. Make sure that you label them so that I know what they are. I'm done. You're on your own. Get your data. Be free. So there's 3 tennis balls up here and 2 golf balls.